All right, so just left off, I'm on slide 14 of the chapter 2, the first PowerPoint in chapter 2. Again, I've already listed, these are the experiments that you're supposed to read about and know. We're going to talk about them a little bit, but you need to know a little bit more detail. Specifically for each one, a general description of the experiment, what were the results that they obtained, and then what did they learn from that experiment for each one of these. So, Thompson's cathode ray, basically he applied a voltage to a sample, it made electrons fly out, so that was the first time that we actually had a sample where particles just spontaneously flew out. The particles that flew out, if you pass them between charged plates, he noticed that the electrons were attracted to the positive plate and repelled by the negative plate, and based on the amount that as the electrons passed between the plates, the amount that they curved in their path, he was able to calculate the charge to mass ratio of the electron. Okay, the units are coulombs per kilogram, but basically it's the idea that the heavier a particle is, the more of a straight line it'll travel in. It's kind of like if you're driving on a curvy road in a school bus, it's real hard to make the bus make the turns everywhere. If you're driving a little sports car, then you can go a lot faster around the curves. It's easier to turn. So that's the idea here. In future experiments, like an electron ends up being called a beta particle, and it gets curved a lot when it goes through the plates. An alpha particle is a much heavier particle, so when it passes between the plates, it's positively charged, so it bends the opposite direction from an electron, and then it's also a lot heavier, so it doesn't turn nearly as much. So based on all those comparisons, that's how they figure out how heavy particles are and how much charge they have on them and all that kind of stuff. All right, so Thompson, he applied a voltage to a sample, electrons flew out, he figured out they were negatively charged, so then he came up with what's called Thompson's plum pudding model, where this is an atom, and basically all that we knew at this point was that the electrons were kind of particles that were stuck in the atom somehow. When you applied a voltage, you can make them fly out. Okay, so the electrons are particles in the atom that contain negative charge, but he didn't know anything about the positive charge. He just said, well, I know the negative charge, we make it pop out. The positive charge is in there somewhere too, in the bulk of the atom, but we didn't know yet where the positive charge was. Okay, so we're still very early in the characterization of an atom. Remember, Dalton just said it was a solid particle, an indivisible particle that you couldn't break up. Thompson said, oh, I can make electrons fly out. So that's the first step toward figuring out all the subatomic particles. So then Rutherford, basically he took a radioactive material that emitted alpha particles, which an alpha particle is actually the nucleus of a helium atom, which is 2 protons, 2 neutrons stuck together. So some heavy metals will emit alpha particles spontaneously, radioactivity. So the alpha particle source just sits there, it shoots out particles sometimes. Rutherford set a thin layer of gold foil in the path of some of the particles. He expected the particles to just fly through, but basically what happened, and again, there are videos about this that are kind of cool. What happened is most of the particles, probably 99.99% of the particles, went straight through like he expected. But there were some particles that for some reason, as they were passing through, they got deflected off at a large angle. And you occasionally had a few particles that when they shot at the foil, they actually came back. Which, based on the calculations of the time, that never should have happened. The particles were moving so fast and with so much mass that they should have just busted through the foil. Supposedly, Rutherford said it was kind of like shooting not a bazooka, but like I don't remember what size, but a huge shell from a gun at a piece of tissue paper, and then it bounced back. That was kind of the comparison that he made when he did this experiment. So, based on that, again, we move forward to where he said, okay, well, most of the atom must be empty space, because, again, when he shot the alpha particle at the gold foil, so this is the gold foil layer right here. When he shot the alpha particle at it, most of the particles just fly straight through because there's nothing there, it's empty space. But every once in a while, there must be some concentration at the center to where when a particle came in, and remember, alpha particles are positively charged, the nucleus, which is what we're trying to discover here, is also positively charged. So when a particle went at the nucleus, if it was straight on line with it, it would actually slow down, and it never would really hit it because the repulsive powers were too strong, but it would slow down, approach it, and then come back. So that's the one that's bouncing back. Or if it just kind of came close to the nucleus, as it came close, the nucleus would repel it, and it would kind of just bend its path. Okay, so based on those observations, that's how Rutherford came up with the idea for the nuclear model of the atom. So we've kind of gone from Dalton's idea, where it's just a solid material that can't be broken, to the plum pudding model, where we apply voltage and electrons can come out, to finally Rutherford's atom, where the nucleus and all the mass and all the positive charge is in the very center of the atom, and then the electrons are all flying around the outside, which is why when you apply voltage, since the electrons are just flying around, it's easy to make them just fly out. So that finally gets us to kind of the nuts and bolts of the chapter, which is if an atom is made up of 3 subatomic particles. If you go into physics, there are a lot more smaller particles than these, but that's going to be a physics discussion, not chemistry. These are the only subatomic particles that we're going to deal with in 1211. But we have electrons, protons, and neutrons. They're all tiny. If you look at their actual masses in kilograms, they have very small exponents here. We're not going to actually use those numbers for anything right now, but we're going to, instead of dealing with those tiny numbers all the time, they basically created a new unit to deal with that size. They said, okay, a proton weighs 1 AMU, 1 atomic mass unit. A neutron, protons and neutrons pretty much weigh the same thing. It's not exactly the same, but it's really close. So they're both about 1 AMU. And then an electron is actually about 1/2000th of the weight of a proton. So technically the mass of an electron is not 0, but it's so much smaller than the other ones that it's not important enough to worry about, so it's negligible, so we call it 0. Okay? But if you really want to get technical, electrons do have a mass. Just remember that. Okay? Anyway, and then charge. Electrons have a -1 charge. Again, these are arbitrary units here. Charge should be measured in coulombs, but it's a tiny, tiny number for each particle. So we know that the charge of a proton and an electron are the equal amounts but opposite charge. So protons are +1, electrons are -1. Okay? And then neutrons have no charge. So then we can take that and we can write an atomic symbol. An atomic symbol, of course, we use the symbol of the element with the abbreviation in the center, and then in the corners, each corner is reserved for a specific thing. So the upper left corner is the mass number. It's the number of protons plus neutrons. The bottom left is the atomic number. That should match up with the atomic number on the periodic table. It's the number of protons in the nucleus. And then the upper right corner is the charge. Basically, if the electrons and protons are equal, then there's no charge. And you don't have to put a 0 there. You can do, if you leave it blank, we assume there's no charge. But then if it's a positive charge, that means that there are more protons than electrons. If it's +2, that means there are 2 more protons than the number of electrons. And then if it's negative, that means there's more electrons than protons. And then finally, the bottom left, if we put a number there, that's telling me how many atoms I have. So if I have a diatomic element like O2, I'd put the oxygen, and then the 2 right here tells me there's 2 oxygen atoms present. So the bottom right corner is always for the number of atoms that we're dealing with. So, in the atom above, how many protons, neutrons, electrons are there? Again, stop and think about it, but I'm going to go through the answers. So the atomic number gives me the protons, so it's 20 protons. If I didn't know that, I could look at a periodic table and figure it out. It's element number 20. All right? Once I know the protons is 20, then I look at the mass number. If it's 42, 42 minus 20 tells me there should be 22 neutrons, because 20 plus 22 makes 42. okay? And then the electrons from the charge, again, if it was neutral, that would be 20 protons, 20 electrons. If it's plus 2, that means that I must have lost 2 electrons, so it's 20 protons and 18 electrons, okay? The number of protons can't change. For calcium, it has to be 20. So if I have to change something, it's going to be the electrons that change, not the protons. All right, so then the question is, can you write the atomic symbol for a nitrogen atom that has a mass of 15? So, real quick. Nitrogen's N. So you write your symbol. The mass number goes in the upper left, so it's 15. The atomic number goes in the bottom left. If you look at the periodic table, nitrogen's number 7. And then if it has a charge that goes up here, well, the PowerPoint just said a nitrogen atom with a charge with a mass of 15. If it doesn't mention a charge, then you're going to have to assume there's not one. So I'm not going to put a charge there. Okay, so that's the symbol for a nitrogen atom with a mass of 15. All right, so now this would be a common test question that you should be prepared for. If I give you a symbol, can you take that symbol and figure out all these values? Okay, so again, stop the video, work through this yourself if you can, and then restart and I'll go through the answers. So the atomic number of sulfur, again, you look at the periodic table, atomic number of sulfur is 16, so that's 16. The mass number can be confusing. If you look at the periodic table for the mass number, there's a good chance you're going to get it wrong. Okay? The mass number on the periodic table is the average mass of all sulfur atoms. And I think it's 32.066. That's the average mass of all sulfurs. Here, we are talking about a specific sulfur atom. This sulfur atom has a mass number of 33. So if you look at the two different things, they may not always agree with each other. And if I'm doing this problem, I'm focused on this atom, the mass number is 33, it goes right here. On the test, about half the class is going to mess that up because they're not paying attention, and they're going to use the periodic table to get the mass number instead of going by the one that was provided in the problem. Okay, the charge, again, it's given to you, it's 2 negative. It's -2 or 2 negative. Formally, a lot of chemists prefer that you do the 2 negative as the way of writing a charge. I didn't learn it that way, but I will say most of the other chemistry faculty at UNG prefer to put the number and then the sign of the charge afterward. Okay, so then protons for sulfur, the atomic number and the protons are the same thing, 16. The number of electrons, if it's 16 protons and it's a -2 charge, that means there are 2 more electrons than protons. So 16 protons, you give 18 electrons. And then neutrons, 33 minus 16 will give you a 17 for your neutrons. Okay? Then if I come over here, this one, there's missing information where I have to kind of work my way through it. The electrons are 36, and the charge is -1. So that tells me there's 1 more electron than protons. So that means it must be 36 electrons, 35 protons. If it's 35 protons, I look at the periodic table, that's bromine. So I know it's going to be bromine's Br. The mass number will be 79. The charge will be -1. And then the atomic number will be 35. So Br, 35, 79, -1 will be my numbers. That's my symbol. Atomic number is 35. And neutrons will be 79 minus 35 to get 44, I think. All right, so we've mentioned isotopes before, but basically most elements on the periodic table, there are different weights that the atoms can have. So like if I'm looking at hydrogen, the hydrogen atom, there are 3 different forms of it. There's hydrogen with a mass of 1, hydrogen with a mass of 2, and hydrogen with a mass of 3. Okay, we know this because we can, kind of like the cathode ray tube, there's a instrument now, it's called a mass spectrometer, where you can send a sample through a tube. You can apply either a voltage, which would be charge plates, or you can apply a magnetic field. But when you apply either one of those, you can make the particle bend, and the amount that it bends is based on its mass to charge ratio. So, you have to take these atoms and ionize them first. Again, this is all higher level stuff than you need to know. But as they pass through, what happens is, if I have like pure hydrogen and I pass it through the mass spectrometer, these three atoms are not all going to bend the same amount in the path. And based on how much they bend, I'm going to be able to see, oh wait, there's three different hydrogen atoms in there, so they must all have different masses. Those are my isotopes, okay? The picture here also has neon, where it's showing three different isotopes of neon that are hitting the detector at the end of the mass spectrometer. So, we know that atoms have different isotopes. The difference between these is the number of neutrons. So I just got to look at these and say, okay, this atom, it consists of one proton. If the mass is 1, that means that there's no neutrons, because one proton has a mass of 1 AMU. So it's one proton in the nucleus, and if it's neutral, that means there's one electron flying around. So that's the whole atom. One proton, one electron, that's it. That's for that one. For this one, it's going to be in the nucleus, one proton and one neutron, both in the nucleus, and then one electron flying around. And in this one, it's going to be one proton and two neutrons in the nucleus, given a mass of 3, and then one electron flying around. Okay? So those are my three isotopes of hydrogen. They behave very similarly in terms of like they can all be part of a water molecule, but you know, the heavier the hydrogen is, the water molecule can get heavier than normal. But the difference is this one is actually unstable, so it's radioactive. When you have a set of isotopes, sometimes some isotopes are stable and others aren't. I gotta cut off my video.